My name is Sai Shri. I build battery packs in Aurora, Illinois. Behind me are 16 sodium ion cells, no lithium, no cobalt, a fundamentally different chemistry. This is part one of documenting something that, as far as I can tell, has never been done in the United States before. A complete DIY sodium ion 48 volt home battery pack built here, tested here, documented completely.
4 videos, 16 cells, 2 rejections, 2 replacements, 1 pack. In this video, everything goes in, everything gets wired, and at the end of this video, we turn it on for the first time. America's first documented DIY sodium-ion home battery. Let's finish it. Quick recap if this is your first video. I'm building a 48-volt, 210 amp-hour sodium-ion battery pack. Not lithium iron phosphate, sodium-ion. In part 1, we unboxed 18 Hikari NaFP cells straight from China. In part 2, we tested every single one. OCV, internal resistance, weight. 2 cells failed. Cell 066 came in at nearly 5 milliohms, double the batch average. Cell 075 was worse, 7.3 milliohms, 3 times the average. Both got pulled. In part 3, we confirmed the replacement cells. Both came in under 1.1 milliohms. Actually, the best readings in the entire batch. All 16 slots cleared. Today is part 4. This is assembly day. This is the Seplos MASON-210 enclosure, designed specifically for 16 prismatic cells in a 16S1P configuration. 8 cells per row, stacked front to back. What you're seeing on the inside walls are FR4 sheets, fiberglass insulation boards. They prevent any accidental contact between the cell casings and the metal enclosure. Every prismatic pack build uses these. You also notice there's a center rail here. This is the cell compression bracket. It keeps all 16 cells clamped together as a unit once everything is loaded. We torque this down later. At the bottom of the enclosure, this is the BMS bay. The Seplos 200 amp Smart BMS mounts here, completely separate from the cell compartment. Clean design. Before any cell goes in, I want to show you the labeling system. Every cell is numbered 1 through 16 based on its position in the pack, S01 through S16 in the assembly map. Each label also corresponds to a row in the QA datasheet, so if anything ever needs to be traced back, I know exactly which serial number is in which slot. Bottom row first, cells 1 through 8, all terminals facing the same direction, positive to the right. This is critical. One cell flipped the wrong way, and you have a short when the bus bars go on. Top row next, cells 9 through 16, same orientation. All 16 in, every slot populated. This is the moment the pack actually becomes a pack. This is the most important check before any bus bar goes on. We're building a 16S pack, 16 cells in series. Series means the positive of one cell connects to the negative of the next, all the way down the chain. Every cell adds its voltage to the total. 16 cells at 3.2 volts each, 51.2 volts nominal. Look at the pattern from above. Red, black, red, black, alternating all the way across. That's your series chain. That's what gives you 48 volts. If even one cell is flipped, you subtract voltage instead of adding it, and you create a dead short when the bus bar bridges the terminals. Every cell gets verified before we touch a bus bar. All 16, correct orientation, we're good to go. These are the green circuit boards you see sitting on top of each row. They have individual wire leads that connect to each cell terminal. This is how the BMS monitors every single cell's voltage independently. Now, the bus bars. Each bus bar bridges one cell's positive terminal to the next cell's negative terminal. That's your series connection made physically. Torque spec for the bus bar flange nuts is 5 Newton meters. That's the Seplos specification for M6 hardware. I'm using a Go-Yo-Jo digital torque wrench set to exactly 5 Newton meters.
You don't want under-torque. You get resistance at the connection, heat builds up, performance drops over time. You don't want over-torque. You strip the terminal or crack the cell casing. 5 Newton meters. Every nut in sequence. This is the Seplos 200 amp Smart BMS. It was pre-configured for NaFP sodium-ion chemistry before this build started. The voltage parameters are already set. 3.95 volts per cell maximum charge, 1.80 volts per cell minimum discharge. Those numbers matter. This is not a LiFePO4 BMS. If you used LiFePO4 settings on a sodium-ion pack, the cutoff voltages would be wrong, and you'd either undercharge or over-discharge the cells. Chemistry-specific configuration is mandatory.
The BMS slides into the dedicated bay below the cell compartment. It mounts to the bracket with 4 screws. Now, the 400 amp fuse. This is your pack-level overcurrent protection, the last line of defense before the power terminals. If anything catastrophic happens downstream, this fuse opens before the cells are damaged. Front panel goes on. P+ and P- are your main power output terminals. CAN bus and RS-485 ports for inverter communication. LCD display top left. This panel is the only thing a user ever sees from the outside. The cell sense harness connects every cell terminal back to the BMS. This is how the BMS knows the individual voltage of each of the 16 cells in real time. Not just the total pack voltage, but every cell independently. If cell 7 starts drifting out of balance, the BMS sees it. If cell 12 drops faster than the others under load, the BMS sees it. This harness is what makes active monitoring possible. The LCD ribbon cable connects the display board to the BMS. It's a dedicated small board. You can see it labeled LCD004-SP that drives the screen on the front panel. Wiring rule: nothing crosses a terminal. Nothing sits loose over a terminal. Every wire is routed to the side and kept away from any potential short path. This is not optional. It's how you build a pack that stays safe. All connectors seated, all wires routed. Pack is internally complete. Let me walk you through the front panel before power on. This is the complete interface panel. Top left, LCD display. This shows pack voltage, current, SOC, and any warning codes in real time. This is what you'll read every day. Center, 4 power connectors. 2 labeled P- and 2 labeled P+. These are your main output terminals. This is where you connect your inverter cables. The dual connectors allow for higher current capacity and redundant connections. Bottom left, CAN bus, RS-485 port 1, RS-485 port 2, and a reset button. The CAN bus is how this pack talks to a Victron, Growatt, Dea, or any compatible inverter. Plug in a CAN cable here, and the inverter reads SOC, cell voltages, temperature, the full data stream. Bottom right, ground lug. Always connect your chassis ground here. This is your safety ground, not a current path. All right, everything is connected, everything is torqued, everything is seated. This is the moment where we find out if we did it right. Pack voltage, 43.14 volts. That's 16 sodium-ion cells sitting at storage state voltage, exactly where we expect them after the QA phase. Current, 0 amps. Pack is at rest, nothing connected, no load. Clean. State of charge, 49.9%, right in the middle. These cells have been sitting since QA testing. That's normal resting SOC for NaFP cells at storage voltage. Warnings? N. None. 0 fault codes, 0 alarms. The BMS powered on, recognized all 16 cells, and reported a clean status on first boot.
This is a live, functioning 48-volt sodium-ion battery pack, built in Aurora, Illinois. First documented DIY sodium-ion pack in the United States. Part 5 is the full BMS configuration. We'll go through the Seplos battery monitor software, set the sodium-ion parameters on screen, and do the first controlled charge. If you're building one of these or thinking about it, the link to reserve a ZERITHIUM SIB-48 is in the description. Early access pricing is still open. Fully refundable deposit. Like, subscribe, and I'll see you in Part 5.